Good morning, everyone. So, our HDL presentation is on the topic energy efficient processor design using multiple clock domains with dynamic voltage and frequency scaling. I'm Tanishka, and the people in my group are Amol Gothi and Harsh Agarwal. So RISC basically stands for Reduced Instruction Set Computer. It is a microprocessor that is designed to perform a smaller number of types of computer instructions so that it can operate at a higher or better speed. The paper that we have chosen, it designs a 16-bit RISC processor which is capable of executing more number of instructions with a simple design, and they've used VHDL, and the design is simulated in Xilinx ISC. The main achievement in this work is that the multiplier unit in and the ALU and the accumulator, it is implemented using Vedic sutras. The main principle used in Vedic mathematics is to reduce the typical calculation of conventional maths to a very simple one, and hence it reduces the overall computational complexity of the whole math. Vedic Mac and ALU are integrated with the other blocks of the processor, and that's how the 16-bit Vedic processor is developed. It reduces the delay by 34% and it saves around 88% power compared to the other conventional processors. Hence, the key features of the designed RISC processor are improvement in speed of operation, reduction in power utilization, and it utilizes less area. This is the brief explanation of a RISC processor system. So as you can see in the diagram, it explains the RISC processor system, and the components of a RISC processor will be explained by Harsh.
So, as seen in the diagram, the components of a RISC processor are arithmetic logic unit. This unit is intended to perform various numbers from using various instruction sets. And this ALU is a very important component of a processor which uses an instruction that and an opcode to perform some operands. Second is the register bank. It is a small set of data holding place. Uh, Arithmetic logic unit stores the result of operation in accumulator, which is placed in the storage register later, and checks the bit and indicates whether the operation was performed successfully. Next, instruction register. The task of instruction register includes decoding the opcode, determining the instruction, determining which operands are in memory, retrieving the operands in memory, then assigning a command to a processor to execute the instruction. All of this is done with the help of control unit, which generates timing signals uh, with the help of a clock that controls various processing elements involving the execution of instruction. Next, program counter. Program counter points to the next instruction to be executed. In the complete instruction cycle, the instruction is loaded into the instruction register after the processor fetches it from the memory location, which is pointed by the program counter. Next slide. Next, control unit. Control unit is an essential part of any kind of computer or system because the circuit generates the timing and control signal for the operation which is performed by the CPU. Here the communication is between the ALU and the main memory because it controls the transmission of signals between the processor, memory and different buses. Memory address register is also called address buffer. The address in the program counter is applied to memory to increment the program counter to the next address so the next instruction can be performed and the memory can be stored into the location. The memory address register is loaded with binary words which point the location to the word in RAM. This location stores the instruction in it. Multiplexer. The multiplexer block works as input selectors. It can control wire, which acts as select lines. So for different select lines, different operations are performed. Next, instruction set architecture. ISA provides the information to write the program in machine language. It also allows translating a high-level programming language to machine language. Below is a 16-bit register frame where starting 12 bits 0 to 11 indicate the address. Next three 12 to 14 are the opcode, and the rest, the 15th bit is the addressing mode. Next slide. Now, why Vedic mathematics Surta? So the problem in the previous methods were signal processing applications require multiplication as a basic operation. So the study in the paper reflects that the multipliers require more silicon area. Also, therefore, they consume more power due to switching activity. So they create longest path via adders and carry. This limits the maximum speed in processor. This creates a limitation of critical paths in processor. So the Vedic mathematics sutra used in the paper is Urdhva Triakbham, which is designed using various sutra for different multiply algorithm. Vedic multiplier has proved to be more efficient using different Vedic sutra. It reduces critical path and dynamic power both. And the use sutra, Urdhva Triakbhyam sutra, is applied to multiplication, which follows the vertically and crosswise pattern. Therefore, the designing and multiplier comparison using various sutra is performed using mathematics algorithm. Now, Amol will continue the rest.
So in this paper, 16-bit processing module is and the output is verified for the given instruction sets. The verification results are presented for complete processing unit with integration of ALU. For this processor, various arithmetic operations have been performed. So as you can see from the table, the Vedic processor uses less number of LUTs and the delay is less, and power required for the Vedic processor is very less as compared to conventional processor. This simulation is carried out using Vedic sutras to perform these basic arithmetic operation. The given input through the select line is for 4 bits. Next slide. As you can see, these operations, basic arithmetic operations, have been performed by using Vedic processor. For addition and subtraction, input is given for 16 bits and the select line is of 4 bit and the output is stored in 32-bit registers. Next slide. In conclusion, we can say that 44% saving in power in case of Mac and that of 12% in case of ALU for Vedic processor, and delay is reduced by 45% in case of Mac and 35% in case of ALU in comparison with conventional ALU and Mac. Hence, the Vedic 16-bit Vedic processor reduces the delay by 34% and saves around 88% power compared to the regular processor. We can say that Vedic multiplier are used for the multiplication to improve the speed and reduce the areas and power budget of the multiplier.